Hi everyone, welcome to chapter 2, 2.1, linear equations and inequalities for SAT math. So to begin the discussions on linear equations and inequalities, we want to first understand what they look like. What does a linear equation actually mean? When are we able to classify a graph or an equation as linear or nonlinear. And this distinction is important because this helps us understand what types of problems require what kind of tools. And so to develop tools about linear equations, we have to first understand how to identify when we can use these tools. And so this is the beginning of your journey. Linear equation. So is this linear? Well, I think you have this, the definition of linear equation is very intuitive, the sense that it's linear, it's straight, right? So surely this graph right here looks straight, so perhaps it is linear. But let's take a look at other possible functions and classify if they're linear or not first. This is not linear, and it is not even a function, and that is correct. If you look at this, for some given x value, so let's say just the origin. So for the x equals 0, we have 2 points that correspond to x equals 0, right? We have y equals around 5 and y equals -6. So because we have 2 points given x equals 0, we have y is equal to around -6 and y is maybe just around -4.5, 4.5. This is not even a function, and the definitions for a function can be found in chapter 1. So of course, this is not a linear function. Is this linear? Well, of course, this time it is a function. As you can see, that there's no overlapping parts, right? It passes the vertical line test, but it is obvious that it's curvy, and because it's curvy, it's non-linear. That is good enough intuition right now to understand and distinguish between linear and non-linear equations. And finally, we have something that looks linear, or at least it seems to approach a linear graph. But can this be classified as a linear function? And that's where we have to step in and formally define what it means to be linear. And again, as you can see, following the same intuition as before, this point here and this general curvature, this is obviously not linear. And that's basically what you have to understand to say that this is nonlinear. You can't really use linear functions and the ideas developed in this section to solve questions like this. Now, let's properly define the definition of a linear function. So the input of this linear function is going to be one variable, and usually, and almost in every case in the SAT, it's going to be x. So you can write this as function f of x, and then because we usually put it on a graph, we equate that to y. F of x equals y. And additionally, the degree of that function is 1. So we can have a function of x such that it is equal to something like x squared plus x to the power 3. The degree is talking about the highest exponent on x, right? So in this case, the highest exponent is 3 here. And so this degree of the function is not 1. However, we could have something like could have something like f of x equals, let's say, x plus 7. Well, what's the degree of this function? Well, obviously, the degree of the function is, well, this is equal to x to the power of 1 plus 7. And so the degree of f of x is equal to 1. And so this is a linear function by our formal definition as given here. So using this definition, we can actually properly check and identify linear functions. Here's a first example. Let me move my screen here. The example is f of x equals 3x plus 7, and I have just given the graphical representation of this, and you can see that, of course, it follows the first and foremost, the intuition that a linear function should be like a straight line. And as can be seen, this is a very straight line. So that is valid, but at the same time, you can look at the degree of this function. It's actually 1, right? Because 3x plus 7 is just 3x to the power of 1 plus 7. The degree is 1. And as can be seen, this function satisfies the vertical line test. So there you have it. This satisfies the definition. This is a linear function. And moving into the next part, a key observation that I want you to make here is that this linear function has a steady incline or a decline, right? Something curvy like this. You can see that it goes up and then it goes down, then you can go up again. It might go down really fast. These are the incline and the decline is not steady at all. But given a linear function, however, if the incline is something like this, then it's going to continue this incline forever. And if it's a decline, then likewise, it will just continue a decline. That is constant. That constant nature will help us. Now we define the slope, x-intercept, and y-intercept. So quickly, the definition is, as can be seen here, the slope is the rate of change of a function. So if f of x is equal to ax plus b, the slope is equal to a. The x-intercept is a point on the graph that intersects the x-axis. So then f of x equals 0, so x equals minus b over a. And the y-intercept is the same idea. It's just when the graph intersects the y-axis, so then x would be equal to 0, so y would be equal to just b. And given that we have generalized the linear function to the formula of f of x equals ax plus b. Let's look at examples and graphical representations. So let's think about the x-intercept. The x-intercept here is when graph is crossing the x-axis, crosses the x-axis. So you can see that happening right here. Right? This is where this red line, the graph, is crossing the x-axis here. Let's just label that. And so the x-axis is being crossed at this green point, and that point is exactly negative 2.33 at 0. And you can see how the y is equal to 0 here. This function, I believe, is y equals 3x plus 7. And so this follows the definition, the theorem from before about the x-intercept, that the value of the x value at the x-intercept is going to be equal to negative 7 over 3. Let me erase everything. Now we talk about the y-axis. Sorry, not the y-axis, the y-intercept. Y-intercept. So this is when x is equal to 0. And as can be seen here, right, this is 0, 7. This is when this red line, the graph, is crossing the y-axis. And so we have this blue dot as our y-intercept. And again, this graph is 3x plus 7 equals y, or f of x. And so it follows from the theorem that the y value of the y-intercept is equal to 7, as can be seen with the blue point there, 0, 7. Okay, and finally, we will talk about the slope here. The slope, well, again, we know that this graph is 3x plus 7. So, simply, the slope is going to be equal to 3. Slope will be 3. This is the rate of change. And to just kind of properly understand what rate of change means, it means for every one value of x, you move some value of y. So in this case, when we say the slope is 3 or the rate of change is 3, we're saying for every additional x, we go up. We gain 3 extra y values. And that pretty much sums up the ideas for rate of change and slope. You can see how the slope then is constant throughout the entire graph, right? We keep moving. So for x equals 0, we have a certain value, y equals 7. Then x equals 1 will imply that y is equal to 10. This will continue on forever. It's ratios, it's proportional. Okay. Now, deriving f of x equals ax plus b. This is an important skill to have because a lot of our techniques can be used in this specific format, the general form, and deriving this quickly will be important. So, starting off with 3 times minus 7 plus y equals 9x. So this is a example of a question you might have, right? This might be a form that is given to you on an SAT, and then you might be told to derive the slope or something. So in that case, well, we don't know anything much by looking at this, so we're going to try to make it into f of x equals ax plus b, or just y equals ax plus b. So given 3 and 9, we know that 3 divides 9, so by cancellation, we have let's write that down. 3 equals 9x. So you just divide both sides by 3. And then you get minus 7 plus y equals 9. Sorry, not 9. 3. Oh, let me get that eraser. Oh no, erase all. Okay. Sorry about that. Minus 7 plus y equals 3x. This is after dividing both sides by 3. Then we can move this minus 7 to the other side to isolate for y, right? Because we want y to be isolated. We don't want y equals ax plus b. And so we can just add 7 to both sides. And this little trick will get us y equals 3x plus 7. And so now you can derive all the information you need about the graph, the x-intercept, y-intercept, and the slope. The slope is going to be 3 because of this coefficient. The degree is 1, obviously, so this is a linear function. The 7, this is going to be the y-intercept as established before, and the x-intercept will be something like negative 7 over 3. So there you go. So really, the process is isolating for your y value. That's going to be important for important to remember and practice this skill.